Okay, so part B of optimization, chapter 3, section 7. So let's jump in. Let's start to challenge ourselves a little bit more. Okay? So let me read the following problem. So it says 2 posts, one 12 feet high, the other 28 feet high, stand 30 feet apart. Now, you can approach these problems however you would like, but normally in conversation, right, when a period would represent some type of pause in the conversation, right? And in a word problem, for me, a period should represent and a comma should represent a pause to make sure we understand what was said prior. So I could read the rest of this, but right now I want to make sure I understand the very first sentence. So 2 posts, one 12 feet high, the other 28 feet high, are stand 30 feet apart. Okay, so now that's not bad. I'm going to see if I can draw that. So I have 30 feet of distance, and it's separating 2 different poles. Well, for some context, we'll just say it's maybe utility poles. So here are my 2 poles. So one is 28 feet high, the other is 12 feet high. Okay, so far so good. Again, no jealousy with my ability to draw. Just calm yourself and let's continue with the problem. So it says they are to be stayed by 2 wires. So hold on. What does that mean, to be stayed? So if we go with the using the context of some type of utility poles, right? So oftentimes if I can get you to value the solution, then you'll value the methodology to get you there. So if you have to, you can envision yourself working for some type of company that is going to be maybe installing and placing utility poles to get communications or electricity to a new region, maybe new development. And the idea is each pole is going to have some type of wire, right, that's going to be staked into the ground that will help support that pole, right? Does that make sense? So there's going to be some type of stake in that in the ground where some cable, so maybe some, I don't know anything about utility poles, but maybe some stainless steel or galvanized steel. I don't particularly know, but I think we got the gist so far. Now, so stayed by 2 wires that are attached to a single stake. Okay. Now, running from the ground level to the top of each post. All right, so let me go ahead and see if I can draw that. So now I don't know where this stake is going to be placed, right? But I know that we have a wire running from the stake to the top of these utility poles, and that is how we are that's how we are staying supporting each of these utility poles. All right, now the last sentence says, where should the stake be placed to use the least amount of wire? Now, this is an optimization problem. As soon as somebody phrases the least amount or the most amount, they are asking for a minimum or a maximum, right? So this becomes a problem of optimizing to be able to find the minimum or the maximum. And as maybe some of you have heard me say before, there's a lot of money to be made. In other words, people will pay you a lot of money to optimize things for them, to minimize their costs, etc. So what I'm going to do right now is give myself just a little bit of room and probably draw this diagram a little bit better. So I know that I have 30 feet running or distance between each pole, right? And you're trying to use the minimum amount of wire that you have to. And if you, again, for context, if you can imagine that you are running thousands and thousands of these poles, 12, 28, 12, 28, the sheer fact that if you can, and you're trying to minimize the costs, that's more profit for your company. So it is in their interest to pay you or pay someone to figure out something as simple as where should the stake be such that the least amount of wire has to be used, right? Okay. Now, the way this game begins, we're going to have to do a little bit better in order to get to an equation that we can optimize. Let's start with some observations. Well, I think we can assume that these are going to form 90-degree angles with the ground. And furthermore, let's actually label the hypotenuses of each of these. Right now, I don't know what they are. So I'll just label, let's say, this little triangle would have a hypotenuse of y, and this large triangle would have a hypotenuse of z. Okay? Now, whatever we do with this problem, I just want y plus z to be the smallest possible number, because that would mean the least amount of material is used for this construction. So let's now go a little bit further and let's start to think about the bases of the triangles, right? So can you agree with me that I know I've labeled the hypotenuses, y and z. I know the height, 12 and 28. But what about the base, right? What about the base of these triangles here? Well, because we don't know where to place this stake, right? In other words, you have to imagine that we are willing to move this stake to the left or to the right, where it doesn't matter to us as long as it supports the poles and minimizes the amount of wire. So we can put the stake here, we can put it here, we can even put it here. It doesn't not matter to us. Okay, so in this case, the way this is going to work is what we do know is the stake is going to be somewhere between 0 and 30, right? It's going to be somewhere between 0 and 30. We don't know where yet. So let's assume that if we decide to place the stake in the ground right here, and we don't know where that is yet, so when we don't know something, we give it a variable, right? We'll call it x. So now my question to you, and I'll answer this question in just a second, my question to you is, if we make the stake x, then what is the distance from here to here? And what is the distance from here to here? How would we label that? So I'll answer that question for you in just a second. Ready? So we would be able to say that the distance, I'll go ahead and chop this up since like this. So the distance from here to here, from the first pole to x, is indeed x. Now, the distance from x to the second pole, that's a little bit harder for students to think about. Well, wherever you put the stake, this is going to be 30 minus x, because the entirety of the distance is 30. Does that make sense? Okay. So part one is done, and part one was just being able to draw some type of mental model. It's either create some mental model or draw some type of sketch, just so we have a good feel for what the problem is asking. And now, part two, or step two, if you will, is the part where you try to find some type of equations that relate these variables. Okay, well, let's start with the primary. Let's start with the thing that you want to optimize. Ready? So y plus z is the total amount of cable that you would have to use. Now, all I'm going to do is just say that y plus z has to equal something. I don't know what that something is. I'm running out of letters, so I'll just call it w. All right, now here in a second, I'm going to label whether that's the primary or the secondary equation. Let's go to the secondary equation. All right, well, what other equations out there would relate to the y and to the z? Let's start with the y. Well, as soon as I drew that right angle, hopefully you were thinking that Pythagorean theorem would help us out. So let's start with the first triangle, right? So this is triangle 1. So Pythagorean would tell us that the hypotenuse squared must be equal to each leg, the sum of each leg after they've been squared. So x squared plus 12 squared. Okay, let me box that in. Okay, so, but that's not the only triangle that we have in this diagram, right? We actually have two triangles. So let's go ahead and set up the second triangle. In this case, we would have z squared is going to be equal to, well, the base is 30 minus x, so that would be 30 minus x squared, and plus the height, which is 28 squared. Okay, I'm going to box this in as well. And this would be the second triangle. Okay, so as you can see, we actually have three different equations that are going to aid us in this problem. Right now, I want to answer the question as which one's the primary? And as I stated in the last video where I wrote these little steps, I wrote them out in a little bit more detail. But the primary is always the thing that you want to minimize or maximize. Okay? The thing that we want to minimize, in this case, is the amount of wire that is going to be used. So, in other words, the first equation is the primary. And in this case, we actually have two secondary equations. Okay, so now we're going to move on to the third step. So as you can recall in the previous video, the goal of the secondary equations is to help you rewrite the primary equation, right? In other words, look at your primary equation right now. W is equal to y plus z. That's one equation. It's explicitly defined in terms of y and z. It's in terms of two variables, right? This is not good for us. We know how to take derivatives of one variable, not multiple variables yet. Okay, so where do we go from here? Well, notice that if I solve the secondary equations for y and z, then I can plug them in, each of them into the primary equation. And that is exactly what I'm about to do right now. So step 3, we're going to solve, and, well, I'll go ahead and do that in the next step. So we're going to solve for y and z. Ready? So if y squared is equal to x squared plus 12 squared, then y is equal to the square root of x squared plus 144. And z is equal to the square root of x squared. Let's see here. I'm going to go ahead and, so I want you to understand, what I'm going to do right now is I'm going to just FOIL the 30 minus x squared out, and also go ahead and evaluate 28 to the power of 2, and then combine like terms. Okay, so if you did so, you would have x squared minus 60x plus 1,684. Okay, it's not that I'm trying to punt on the steps. It's not that I'm trying to get out of showing you work. At some point in time, I have to just assume common knowledge. I have to assume that you can FOIL that and combine like terms, right? Now, why did I not have, when I took the square root of both sides, why didn't I have my plus or minus? Why did I just use the principal root? Well, I think it's quite obvious that although mathematically y is equal to plus or minus the square root of x squared plus 144, the application, right, is dealing with lengths, and there's no concept for a negative length. It doesn't make any sense. I mean, you can define in a game of football that you've lost 5 yards on a play, but that just means that you just arbitrarily decided that the scrimmage line was 0, and you defined one direction to be positive numbers and the other direction to be negative numbers, but in reality, you lost positive 5 yards just in a direction that you called negative. There is no such thing as negative length. So here we are with our two equations. So step 4 is going to be substituting into the primary. All right. So here we go. So let me write. The old primary equation was W was equal to Y plus Z. And here is your new primary. So actually, let me give myself a little bit of room. So the new primary equation is going to be W is equal to the square root of x squared plus 144 plus the square root of x squared minus 60x plus 1684. Okay, now do you notice that at no point in time in this calculus problem have we done any calculus? Right? Does it make sense to you that all of this work up front was to rewrite the primary equation. And now, just to appreciate what you've done, look at your primary. It used to be that if I wanted to know the total length of wire to be used in this problem, I would have to know the length of z plus the length of y. Do you know what you have now? Just appreciate this for a second. Now, if I want to know the total length of wire, all I got to know is where you put the stake in the ground. All I need is x. That's actually pretty awesome when you think about it. But we now want to answer the question. So now is when we need the calculus. So I'm gonna grab W. We're gonna give ourselves a new page. Okay, so entertain yourself for just a second. And finally, let's go to the fifth step. Ready? So now we need calculus. So now we want to take the derivative, it's W prime, or the derivative of W with respect to x. And here's what I'm going to do. Here's what I'm going to do for you. I know that I've already trained you on how to do derivatives. So I'm going to write the answer. But I'm also aware that it's really frustrating when you don't know how to get through the steps of a derivative when your professor is moving on to try to finish the problem. So what I'm going to do is I'm going to write the derivative for you, and then I'm going to scroll to another page and show you my work that I used, okay? So I'm actually going to do that twice in this problem. Right now, I'm going to go ahead and write the derivative. So here it is. So x over the square root of x squared plus 144 plus x minus 30 over the square root of x squared minus 60x plus 1684. Okay, so I'm gonna go ahead and scroll to the other page so I can show you the work. Okay? So I'm not going to stay here very long, so if you need to, you can pause the video, but this is the work for how you would go through and take that derivative, and it's just a mixture of chain rules, nothing too, and then rewriting, okay? So I'm now going to go back. If you can always pause this video to walk through that if need be. Okay, so now what we want to do is take our derivative and we want to set it equal to 0. So we're going to set the derivative equal to 0. Now, many times when we're looking for critical numbers, remember it's where the derivative is equal to 0 and where the derivative does not exist. In this case, in these optimization problems, I want you to just focus on setting the derivative equal to 0 in order to help you find your minimums and maximums, okay? So as of right now, let me grab this. So here is me setting my derivative equal to 0. All right, and I'll just go ahead and make that a little bit cleaner. Okay, so again, what I'm going to do is skip to the next page to show you the the algebraic work, right? Because listen to me, your calculus is done, okay? Like once you got here, you have done all the calculus that you needed to do to answer this question. The rest of this is just algebra. But if you ask anyone who's ever taught the calculus sequences, don't let it fool you. The hardest part of calculus oftentimes is the algebra, right? The trigonometry and the algebra. So those preliminaries. But what I'm going to do is I'm going to go ahead and answer the question of what x equals if you were to solve this. And x is equal to 9 as well as negative 22.5. But I won't leave you hanging. I'm going to go to the next page, and I want to show you the algebraic work of how I actually was able to solve for x. Are you ready? So let me do that right now. So in this case, hopefully it's somewhat, well, I'll tell you what, I'll finish it. I don't think I actually finished it from here. So what you can see, and I'll hold this here for just a second. You can see what I'm doing from here is I'm clearing the fractions, in other words. So I'm multiplying both sides of that derivative equation by the least common denominator, right? So that's the least common denominator, and I'm basically multiplying both sides of that equation by that least common denominator. I do that only so I can clear the fractions. So that takes me to here. And that's just the same derivative without all the fractions. Okay, at this step, I had it set equal to 0, but I'm grabbing one of the terms and bringing it to the other side. And I'm starting my algebraic work to try to solve for x. So what I thought I had completed for you, I obviously did not. So I said I would show you, and I'm going to do that. So let me take you the rest of the way from here. Ready? Okay, so as of right now, my goal is I want to try to get rid of these radicals. So what I'm going to do in this next step is I'm going to square both sides. Right, so square both sides. So if I square both sides here, let's write what that looks like. Well, the good thing about squaring a square root is it will get rid of that radical. So that leaves me with x squared. And now let's get rid of that radical. So that would just be x squared minus 60x plus 1684. And then this is going to be equal to that's going to be 30 minus x squared. So now that's squared. And now let's actually get rid of that last radical. So times x squared plus 144. Okay, so squaring both sides got rid of my radicals. Oh man, so now we have quite a lot of distributing, foiling, and distributing, right? So this next line is I'm gonna write for you is just a whole lot of foiling and distributing. But when all is said and done, we're here. So this would be x to the power 4 minus 60x cubed plus 1684x squared. That's going to be equal to, the right side is the messier side. So all of that's going to get me to x to the power 4 minus 60x cubed plus 1044x squared minus 8640x, and then plus, I'm going to write that plus symbol below here, so plus 129,600. All right, I don't have a lot of space to be able to fit all of that in there and make it still be readable. So you can work through that if you decide to on your own, but I get it. That is a lot of, that's tedious. That's a lot of extra distributing and foiling and things. But now if you just start combining like terms, and so I'm now going to combine like terms and set everything back equal to 0. So that gets me to here. 640 x squared plus 8,640 x minus 129,600 equals 0. Right, so I had it set equal to 0. I moved one of the terms, right? I moved one of these terms here to the other side so that I could square both sides, get rid of the radicals. Now I set it back to 0 again. All right, does this factor? It does. And this is what it factors to be. So I can factor out a 320. And what would be left would be an x minus 9 multiplied by 2x plus 45 equals 0. And look, I know that's a lot of work, but I said that your solutions were x equals 9. There's where the 9 comes from. And x is equal to negative 22.5. And that's where that value comes from. Okay, so let me go back to where I was, where I'd left off. And now, at least you can see how I arrived at these 2x values. Does it make sense to you that I'm going to throw away the negative 22.5 because I don't, that x is supposed to represent where I should stake the two wires. I don't know what this negative 22.5 would mean in the context of this problem, so we're going to throw that out. And what's left? What's left to do? Well, what we're left with is x equals 9. And now let me go back to the picture, okay? So right now, what we have determined, or what we are about to determine, is where to put the stake in the ground. So what are the potential places? Well, we can remember that minimums and maximums can exist at the critical numbers, which is the 9, but it can also exist at the boundary points, which would be the 0 and the 30, right? So maybe I could save the most wire if I actually put the stake all the way over here, starting at 0. Or maybe I should place the stake at 30, and that would save the most amount of wire. Otherwise, it's going to be 9. So how do we find out which of those options, which it is? Well, we're going to take x equals 0, 9, and 30, and we're going to figure out which one of those produce the minimum amount of wire. So I'm going to plug those in, but can you agree with me that, man, there's a whole lot of work here? Where do I plug them in at? Well, you want to plug them in to W, the new equation for W. So if I plug in 0, if I plug in 9, if I plug in 30, this would be W of 0 is equal W of 9 is equal W of 30 is equal. And now listen, as long as they're all safe, I don't care which one, where I put the stake. I'm just trying to save my company money so I can get my bonus. With me? So if I use 0, we would have to have 53.04 feet of wire. Okay? If I put it at 9, we would need 50 feet of wire. And if I put it at 30, we would need 60.31 feet of wire. Do you see how we found the minimum? The minimum amount. So we're going to go back over here to the picture. So tell your guys to make sure that they put the stake in the ground at 9 feet from the first pole. Because if you put it at 9 feet, when X is 9, we're only going to need 50 total feet of wire to stake those two poles. Okay, so this is optimization. What I'm going to do is, since I know that is a lot to digest, so I'm going to do this in 3 parts. So I'm going to go ahead and take a break. And I will see you in the last video, and we'll just do a few more of these just so you can have a feel for the various optimization problems. See you soon.